Okay, as a follow-up video on speed, we're going to talk about that average versus instantaneous issue a little bit further, and we're going to use an example here to hopefully illustrate that. Remember that speed ignores direction. So as objects change direction, the speed, the distance keeps accumulating. It keeps getting bigger and bigger. The path length doesn't really care what direction you're going. And so the speed is often going to be a better representation of the actual motion of the object. Alternatively, velocity in an instantaneous sense gives us a very good idea of the motion of the object, because it's going to deal with what direction the object is going as well as how fast it's going that instant. The problem with average velocity is that as the object changes directions, the actual speed that the object is traveling at will get lost in the fact that the position isn't changing as much as you would think it would be given how fast the object's going, because that change in direction lowers the overall position. Let's look at an example. Jogger takes 58 seconds to complete one lap of a 400-meter track. Compare the runner's average speed and average velocity. Why would the instantaneous speed and velocity be more similar? So here's the jogger, and he's going to go all the way around a 400-meter track. 400 meters is like a quarter mile on the off chance that anybody's watching this in America. He's going to do that in 58 seconds. So what that means then is that he's traveling a total distance of 400 meters, while at the same time he has a displacement. Well, here he started and here he finished at the same spot, and so he has a displacement of 0. If we look at that in terms of the speed of the object, of the guy, we get delta D over T, which would be 400 divided by the 58 seconds, 400 meters divided by 58 seconds, which works out to about 6.9 meters per second. Alternatively, if we look at the velocity in an average sense for the whole run, then we're going to get 0 over that 58 seconds, which is going to work out to a velocity of 0. Again, this is obviously a more meaningful number. This is how fast he's actually traveling around the outside of that track. This 0 doesn't really have a lot of meaning. If we were to try and consider the instantaneous velocity, we don't have numbers to work with that. But just imagine the guy as he's running down the backside of this track here. Here we might say he might be running at, let's say 7 meters per second, and let's call this the west direction. In that instant, or the instantaneous velocity might be 7 meters per second west. We can see, I'm just making up that 7 as something close to 6.9. But what we can see here is that speed and velocity in an instant are much more similar than they are in an average sense, because in an average sense, changes in direction can cause the velocity to not reflect the overall speed of the object. Okay, kilometers per hour versus meters per second. So let's say, for example, that you have a number like 60 kilometers per hour. Say a car is traveling down a road or something like that, and you want it in meters per second because you want to use it with other physics equations. If I take that and I recognize that in 1 kilometer there are 1,000 meters, then I can recognize that there are 6,000 meters being traveled in every hour. Now, as a second step here, I can recognize that in 1 hour there are 60 minutes, and in 1 minute there are 60 seconds. So if I divide that number by 60 twice, I can see that that means that I'm traveling at 16.7 meters per second. Now that's a lot of work. We don't want to do that in every question. So what we need to recognize here is if we're going to go from kilometers per hour to meters per second, what we're going to effectively end up doing is dividing by 3.6. We multiply by 1,000, we divide by 3,600. The net result is we divide by 3.6. Alternatively, let's say we had something like 10 meters per second. Again, maybe this is a car or something, it doesn't particularly matter. And I want to go to kilometers per hour. Well, the first thing I'm going to do is I'm going to figure out how many meters I'm going per hour. Here I recognize that there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. And as a result, this object is going to move 3, 6, 0, 0, 0 meters per hour. Now again, if I recognize that in 1 kilometer there are 1,000 meters, I can see that this is actually going at 36 kilometers per hour. So instead of dividing, if we have it in meters per second, and we want to go to kilometers per hour, we multiply by 3.6. Car travels 50 kilometers an hour for 90 seconds. Determine the distance traveled by the car. See, and here we have a situation where we have a speed in kilometers per hour and a time in seconds, and so we can't mix those two units. And you might be looking at it and saying, well, that time of 90 seconds, wouldn't that be easier to put that into hours? But 90 seconds works out to some unreasonable fraction of an hour. It's just not that good of a way to do it. So this is a situation where we want to take our speed, which is 50 kilometers per hour, and change it to meters per second. So again, I can go through this whole process one more time, but the reality is all we're going to end up doing here is dividing by 3.6. So that works out to 13.9 meters per second. I have a time of 90 seconds. And now that I have common units, if I'm going to do my speed is equal to my distance divided by my time, then 13.9 equals distance divided by 90. And to solve this equation, I can multiply both sides by 90. And that's going to work out to 1,250 meters. So over those 90 seconds, you're going to travel 1,250 meters. So that's why we might have to convert kilometers per hour to meters per second, and how we do it if we have to.